Welcome to the AI for You Cafe today with the speaker Claudio Semini. He's the head of the Dynamic Leg Systems, short DLS lab at Istituto Italiano di Tecnologia. And I do not speak Italian, so I hope Claudio forgive me. You will say it better.
You can call IIT.
With his talk on Project VINUM towards automated pruning of grapevines. My name is Carmen McWilliams, and I'm the moderator and organizer of the cafe. I'm the director of the company Grassroots Arts and partner in the European AI for You project. Please take notice that this session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speaker expresses his personal view and opinion. This is not necessarily the official AI for You project opinion. So just for the introduction, great you're all there. I will now shortly say what the cafe is about, and then I give soon the floor to Claudio. The Web Cafe offers a series of live web sessions which is taking place regularly. The cafe is an online forum to gain insight into the European AI scene. Participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. Important, this is an interactive session. You can write questions in the menu, in the panel on the right side. You see a panel. You can write it down. I will read your questions after the presentation to the speaker. And now we're coming to the main highlight of this cafe. Our speaker today, Dr. Claudio Semini, is the head of the Dynamic Leg System Lab at Istituto Italiano di Tecnologia that developed a number of high-performance hydraulic robots, including HYQ, HYQ2 Max, and HYQ Real. He holds a master degree from ETH Zurich in electrical engineering information technology, and he spent 2 years in Tokyo for his research. Master thesis at the Heroes Lab at Tokyo Tech and staff engineer at the Toshiba R&D Center in Kawasaki, working on mobile service robotics. During his PhD and subsequent postdoc at IIT, he developed the Quadruped robot HYQ and worked on its control. Since 2012, he leads the DLS lab. Claudio Semini is the author and co-author of more than 100 peer-reviewed publications in international journals and conferences. He's also a co-founder of the Technical Committee on Mechanisms and Design of the IEEE RIS Society. He is and was the coordinator and partner of several EU national and industrial projects. His research interest includes the design and control of highly dynamic and versatile legged robots for field applications in real-world operations, locomotion, agricultural robotics, and others. A pleasure. It's really impressive, and a pleasure to welcome you, Claudio. And I will now give you the floor. Now you can introduce yourself and correct the name of the institution. So I'm giving you the floor one moment, and here I make you the moderator. So now you are the moderator, and great, I see it.
Okay, great. Can you see my screen already?
Yes, perfect.
Okay, so I put this in full screen. I move down the GoToWebinar. All right. Yes, thanks, Carmen. Thanks a lot for the invitation to this nice webinar series. I'm really interested and excited that I can introduce the project VINUM here. My name is Claudio Semini, and I'm from the Istituto Italiano di Tecnologia. You can also say it for short, IIT. Today, I will talk about towards automated pruning of grapevines. And to give a little bit of my background to you, I'm an expert in robotics. So my lab has almost 15 years of experience in the development of quadruped robots, so robots with 4 legs. We have developed a number of different prototypes over the years, and later in the talk I will show you a bit of videos of the capabilities of these machines. The majority of my team members are actually working not on the mechanical design of these machines, but on control, planning of the locomotion, of the balancing, of the foothold selection, of the whole body control, perception, slam aspects that you will see and are relevant for this talk as well. Okay, but a few words about the applications of quadruped robots. So there's a list of 4 here. There's more, but I think these are the 4 key ones. I'm working in a project that addresses disaster response robotics. Then today we'll talk about precision agriculture, space. I'm involved in a European Space Agency funded project to bring legged systems onto Mars or Moon. And then most of today's commercially available electric quadruped robots are currently being tested in pilot studies for inspection and surveillance in construction sites, oil and gas, tunnels, and so on. But today we would like to focus on the agriculture. And in particular, I would like to introduce the project VINUM. The project VINUM has started in 2018. This is a 5-year project, and it has as a goal the automation of winter pruning of grapevines through AI, data, and robotics, and also, of course, the knowledge of the grapevines of the viticulture. The partners in this project are the IIT in Genoa, that's where I'm based now, and the Università Cattolica del Sacro Cuore, the Uni Cattolica, if you want, that is located in Piacenza. And with this project, we want to combine the robotics and AI aspects with the expertise of the grapevine, of the viticulture, and then create this machine that can do automated winter pruning. A little bit more about the teams that are involved. Inside IIT, there's 2 teams that are involved. There's the team of Fei Cheng and Darwin Caldwell that are experts in robotics, manipulation, AI, and they're the driving force behind the whole, let's say, image processing and manipulation aspects of this project. Then there's my team. I'm leading that together with Victor Baroswal and Michele Focchi. Victor Baroswal is specifically involved in this project here as a leading function as well. And we're experts in quadruped robots. And on the right side, we have experts in viticulture, so in the grapevine science. And these are Professor Matteo Gatti and Stefano Poni with their teams that are collaborating with us on this VINUM project. Okay, so let's have a look at automation in general. Automation in different sectors has advanced at different paces. So for example, as we all know, the logistics sectors has seen a massive improvement in efficiency thanks to robots, and we can see here in the video on the top left how these shelves in Amazon or other fulfillment centers get brought to the workers that then fill in the boxes. And this has massively reduced the costs, and that's how we can order Amazon packages whenever we want, and we even get them the next day. Then automation, of course, in factories like the car manufacturing factories or the food packaging have seen a lot of speed up and a lot of automation in the last decades, actually. Then, of course, also in unstructured and more dangerous, hazardous environments, robotics is already well established. Of course, all the rovers that have gone to Moon and Mars, and then also underwater robotics, where you can't even send people because it's so deep and the pressure is so high, or then demining robots that can go into bomb disposals and other hazardous application. But then if we now move into agriculture, the automation there hasn't really been established as much as in other sectors. And mechanization, on the other hand, has been already well established. So I would like to distinguish between the mechanization, where it's the not yet automated but mechanized. So these are machines like this carrot harvesting machine. I haven't turned off the sound here. This carrot harvesting machine here can harvest hundreds or thousands of carrots in a short time by just running through the field. And this, together also with cucumber and tomato harvesting machines, other harvesting machines, have increased efficiency and reduced costs in agriculture a lot. And so this mechanization has also entered the vineyard. Today we want to talk about grapevines, so the vineyard. Here there's different machines that are used to do certain operations throughout the year on the vineyard. For example, there's weeding and mowing that are attachments to tractors. They're pulled and they go in between the rows into the weeding and mowing, or tilling. And spraying is done with these tractors that have these sprays to spray from both sides onto the leaves and the plants. Leaf trimming as well. The tractor just needs to drive through the rows, and then it cuts the leaves in shape again. Harvesting here, the grape harvesting machines exist, so harvesting can also be automated in the vineyard. This is a mechanized solution that shakes the grapevine trees a lot, and then all the berries and the clusters, they fall down and get sucked up and then brought over through a conveyor belt to a truck where all the grapes are collected. And you can see that a filter brings out the little branches and leaves so that only the berries remain. This is only possible for wine grapes. So grapes used for wine, you cannot do that for table grapes, of course, because the nice looking cluster is what people want to buy, not just the berries. And they also get damaged, the berries, in these very brutal mechanical harvesting. So if we look at now robot prototypes in vineyards and their projects, then of course we first need to mention drones, because drones are quite well established already. They can fly over vineyards or any other agricultural fields to provide multispectral images, prescription maps, high resolution maps that then allow in decision support systems to optimize the use of irrigation, the use of spraying, fertilizer, pesticides, and so on. And in the end, helps to create more sustainable agriculture. So this is really important. On the other hand, the ground-based vehicles here, I just show you a selection of a few. These are, for example, Bacchus, TED, and VT Rover from French companies. These are prototypes that are used for weeding, mowing, and sometimes also tilling and maybe spraying in the future. You can see the characteristics of these machines. They also have this shape that can have keep one row of grapevines in the middle of the plant, in the middle of the machine. Another machine here is an automated tractor, so it replaces the human driver, and it can pull whatever existing tools there exist for tilling and cutting and spraying. And this one here is an agri-robot. This is a weeding robot from Italy. And then there's a number of university-based projects. They usually use a bit smaller machines with a lot of different kinds of sensors, and they are used for monitoring, yield estimation, and other types of important sensing. So if we have a look at what the EU has been doing in terms of EU projects in the past years and in the current years, we see a number of projects on vineyard robotics. And I'm just showing a few here. There's Wine Scout, Grape, Vinbot. These robots roll through the grapevine vineyard rows, and they use sensor measurements to acquire data on the state of the grapes, on the state of the soil, on the state of the temperature, irrigation, and so on, to optimize then the use of when to use the tractor for spraying, trimming, cutting, and so on. There's also a few examples of recently started EU projects for vineyard automation. I would like to mention especially Canopies, which is a project that started this year, which has mainly as a task the collaboration between the workers in the grapevine and the machine itself. And here the machines are helping to carry out of the row to the truck the harvested grapevines, maybe that the humans harvested, and some of the tasks in the vineyard will also be done directly by these robots. Then there's the Bacchus project. This is a bimanual robot development for table grape harvesting, and then Flexig robots that have different types of agricultural applications, but one of the pilots is about grapevines, and that one is about transporting the grapes out of the rows. So we've seen different types of operations that are done with these machines and robots. So if we have a look at the table of annual vineyard operations, we can see on the left a few that we've seen before: weeding, mowing, trimming, and so on. And if you see the ones that are marked in green, they have a lot of, the numbers here mean how many hours per year and hectare have to be put in human labor. So the green one are the most labor intensive operations, the harvesting and the winter pruning. Of course, we see if we use a mechanical harvester, then this time is extremely reduced. So this is for the wine grapes that I mentioned before. But if you need to do manual table grape harvesting, then that's a very, very time consuming operation, a very expensive one. Winter pruning, on the other hand, winter pruning is the second most intensive one, and you can do some sort of automation there, but we will have a look now at what is possible and what not. So winter pruning is a very labor intensive operation that is mainly done manually by experts, people that know the rules on how to do the cutting. You can pre-prune the grapes with a machine. The tractor can go and just cut at a certain height all the canes. That helps, but the finishing of the precise cuts needs to be done by hand. And I'll explain soon why. Because exactly there's rules that need to be followed, so that in spring then the shoots come out in the correct way, so that then in summer the grapevines have the optimized quality and quantity. So there's different techniques to optimize that. And at the moment, more and more there's a shortage of skilled labor. People don't want to do this anymore. It's a tough work, and it's also a work that needs a certain training and a certain skill. So it's harder and harder to find these people. Now, there have been several projects that address winter pruning of grapevines and want to do an automation with that. Most of all, in Australia, there has been many years of efforts to create this kind of container on wheels that can be pulled. I call it container because it's rather big, with 3.5 meters length and 2 meters width. Inside, there's a controlled condition where you have artificial lighting, so that then when this container rolls or gets pulled with the tractor over the grapevine rows, it has a controlled condition for the background and for the lighting, so that it helps the image processing. And then there's this manipulator arm that has a mill end that can then, instead of cutting, it does a milling motion to prune and to cut the canes. Now, in the US, there has been years of efforts as well around universities and the company called Vision Robotics, and they have developed a similar, let's say, container or little house that gets pulled over the grapevine row, and they use blades. These are normal pruning scissors that get used to do automated pruning. But I haven't recently found any news about this Vision Robotics project. I don't know what happened to it. So before entering too much into how we're doing the automation of the winter pruning, I need to spend a few slides on how the winter pruning, what's a little bit the knowledge to know about that. And there's different types of pruning. In Italy, where the soil and in the more southern region where wine is grown, grapevines are grown, we're using mainly Spur, Cordon pruning, or Guyot. And the Spur pruned Cordon on the left side. So the Cordon is this main branch, let's say, of the wine. That has the separate canes and spurs that come out, and they have to be pruned in a particular way. And that's the one we're addressing. There's another one called Guyot, and here in winter, when all the leaves are falling down, you're cutting the main branch of the previous year, and you take the newest, the cane that is closest to the trunk, and you bend this down, and this becomes the new Cordon for the next season in spring, when then the shoots come out and the new branches are growing. So we're focusing on this spur pruned cordon, and we need to understand what are exactly these rules. And so before winter pruning, we see these long canes, and after winter pruning, they are cut in a particular way. And if we have a closer look at that, then we can see that depending on how old that cordon, how old that plant is, it has wood that is several years old. And we can always distinguish between the permanent cordon, this one stays, this is the horizontal main branch, if you want, of the plant, and then there's the 1 year old, no, the oldest, the 3-year-old wood, and then the 2-year-old wood, and then the canes. And if you cut them in a proper way, then the next year you have exactly 2 branches again coming out, and that's the ideal case. So you need to make sure that if we have a look at the plant organs now, because this is what we need to understand, and that's what the machine, our robots, need to understand as well in the end. We need to have a look at these different plant organs. We already had the main cordon. This one is called the arm. That can be several years actually. And then the last one is the spur. And then the canes and the nodes are where the new shoots are coming out. And the cutting rule here that we want to implement and want to follow are get rid of this the half of the spur with the other cane, and then keep only the 2 spurs, the 2 nodes that are closest to the arm and main cordon. And this has a specific reason, because if we start to cut, for example, here, then we're starting to get a bigger and bigger arm spur. And over the many years, this becomes a big cluster, and you start to have the grapes growing in a more random way. And this way you have a controlled growth, and this helps not just for automation, but this helps in general for keeping and managing the grapevines. Okay, so let's dive into VINUM. VINUM has 3 key pillars. There's AI, data, and robotics, and I would like to go through them now. First of all, AI and data. If we have a look at the VINUM pruning pipeline, so this is the algorithm, if you want. This is the pipeline that we are following through from the navigation to the cut. So first of all, we're approaching the grapevine. Once we're there, we're getting the arm with the camera out, and we detect the spurs, and we do that with a neural network that extracts the potential pruning regions. We will see a little bit more about that later. Then the robot approaches the spur. It takes a high resolution image of the spur. It does a machine learn. It runs it through a neural network that does a segmentation of these 5 classes. And then once we have the image segmented, then a graph structure can be overlaid, and based on this tree graph structure, we can then extract the pruning rules that are desired by the farmer, or by this particular pruning technique. Then from the 2D points, we get the 3D points, and can then do the manipulation approach and cutting to the final cut. Now I would like to focus more on the segmentation, the graph, because this is more related to machine learning, and I thought this is most interesting for today. So to work properly in this machine learning environment, we need to have a data set first, of course, and we have our partner at University Cattolica in Piacenza. They have this so-called simulated vineyards, which has alive grapevines, but they are in pots instead of the field. And like this, they can also shift them around or reorient them. So based on this simulated, inside this simulated grapevine, a data set with many high resolution images was captured, and then these pictures were annotated by viticulture experts, which are from Uni Cattolica, and they were annotated to have these 5 classes in a segmented in the image. So basically, if you're not familiar with that, with the mouse, the people need to carefully draw around a line around the class of that segment in the image and then label it accordingly. So we have in pink, in purple, we have the main cordon, we have the arm in green, we have the spur in red, and the canes in brown or orange, and then the nodes are in light blue. And this is how they get annotated. And basically, the people in the collaboration here in the VINUM annotated 148 images. They're split 80-20% for training and validation, and they have recently been published on Zenodo. This is an online platform where data sets can be published. So if you're interested in downloading that, then go and have a look at the or type grapevine organ segmentation, and you will find it immediately. There's also a paper related to that has been recently uploaded by Miguel to ArcSci. It's currently under review. In terms of the segmentation network, here we're collaborating with NVIDIA in Italy, and it has been decided that it's best to use a mask RCNN, and we're using the ResNext 101 backbone here. There's 4 CPUs used for the trainings, and the hyperparameters are following. The batch size is 4, the base learning rate is 0.00025, and training iterations are 50,000. This corresponds to around 675 epochs. And so you can see the result here in this particular case here. There doesn't seem to be an arm, so there's no green areas, but there seems to be the spur and then the cane and the nodes, and that's the most important thing. Based on that, the graph can be generated. So the plant graph can be generated, and then the potential pruning points can be extracted. So basically what is done here is that knowing these segments, in the base of each segment, in the root of the segment, where it attaches to the previous one, that's where we place a coordinate frame and start to label that. And that's basically shown here with these spheres. And then depending on what class this segment is belonging to, there's a different color also for the tree node. And building up this tree, we can then apply the pruning rules. Here in this case, for example, the rule was cut after 2 nodes and then set the cutting point. And you can see this illustrated with this red line and circle. This is here now, again, a close-up of this graph. You can see here again the different types of nodes of this plant graph, and then you can see the cutting points are identified in the middle of 2 nodes, because even if you then have a bit of a deviation with your manipulator arm that places the scissors there, you're safe and you're not cutting into the nodes, which is something we want to avoid. All right, so here are a few more pictures of different cases. You see the background here is what it is. This is the background in the simulated vineyard. You have different plants in the background, but the network is very good at distinguishing between what is in front, what is in the center of the attention, in the image, what we're mainly interested in, and disregard the background. So now that I've explained the AI and data side, or at least I gave you a glimpse in a few aspects of it, I would like to talk about the robotics side. And in the robotics side, we have developed a prototype. This prototype consists of electric shears. These are commercial electric shears that we modified so that we can automate the opening and closing of the blades. We're adding a RGBD camera, so we get the RGB images with depth information as well. We're using an Intel RealSense here. We have a manipulator arm in white here. We are using an onboard computer. This is just a normal laptop with GPU. And then we have a mobile base that in our case is a Neobotics MP500. So this works well on these wheels in the lab, but not so well in the vineyard. We've never tried. That's why we then will use more let's say the platform with higher mobility, that is the legged system. But I will talk about this in a few minutes. So here's a close-up of how the camera and the clipper is mounted at the end effector of the arm. Now, earlier versions of that, already in 2018, have been mounted on a bench top, and we can see here in this video how the robot is first scanning the vines. So it does a scanning motion with the camera from left to right, and then it runs the neural network that extracts the potential pruning regions. You can see that on the top left. Wherever there is a spur, a potential pruning region, there's a bounding box put around. And then based on that, we started to approach the vine. In 2018, we didn't have the rules implemented yet, so it just went to the cane to prove that we can approach it. And this was the first prototype of an automated clipper. Then in 2019, there was the mobile base as well. The robot can approach the vine. You see here we're in a lab environment at IIT. This vine here is dead. We have just strapped this onto this aluminum profiles. And because we don't have many of these plants, we got them from University Católica, we don't cut them. We just approach with the scissors and then go back, because we want to keep this plant intact. Then 2020, there was not much experiments happening, but then in 2021, in March, we went again to Unicatólica to do a live demo. This was a demo that was broadcast and then shown in the national news. And we can see here, we put 3 of these grapevine pots on the table. We use a table here because the mobile base is too high, so that the arm is too high to cut this on the ground. With the mobile legged robot, this is then not a problem anymore, because the mobile robot can move up and down. It is also a bit lower. But here on the right, we've seen automated pruning examples. Here the arm is approaching the cane, and then according to the rules is then doing the final approach. This is not so fast yet, but can be optimized. This is then performing the cut, and the cane is sort of loosely falling down here. So this was the demo back in March. Now, a similar demo with that system was done in 2020, and here we were briefly addressing, just for a proof of concept, also table grape harvesting, because we had this system already. We needed to train another neural network that can recognize the clusters, and then the peduncle, which is the stem on which the whole cluster is held. And then thanks to this gripper here in the bottom right that we modified to insert the blade, we can cut and hold the whole cluster, so that then the whole cluster can be put into a box. And there was also an algorithm to quickly understand where it is free in the box, so that it can then put the grapevine into the correct location in the box. But this was just a proof of concept that I thought was interesting to show you here, because once we have a system like this going with the camera, the end effector tool, the arm, the mobile base, the neural networks behind, this can be scaled into different applications in the grapevine, but then also different type of fruits in the future. So let's return back to the project VINUM. I've mentioned the first part about robotics. Now, actually robotics, I have to divide that into 2 parts, because robotics is not just about the manipulation aspects, but it's also about the navigation aspects. And I mentioned this already before. Our intention here is to not use a wheeled robot. We can, of course, use an outdoor rugged wheeled robot with good tires that can go over moderately rough terrain. But our idea and our novelty here is that we want to use a legged robot to do that operation, because the legged robot has different advantages. It can go even up and down steps and stairs into very steep grapevines. It can even step over tubes. Maybe there's an irrigation tube that was left over somewhere, or maybe there's things we should not step on, and that already makes it very difficult with wheeled or tracked vehicles. So the idea is to use high-key reel. And why the 4 legs? I mentioned just now a little bit of the advantages, but then here's also 2 quick videos to show how wheels, even big wheeled machines here, or smaller tracked vehicles can get stuck even in relatively simple environments. On the other hand, nature with 4-legged animals here, the cat and the dog, but then also goats, horses, they're amazing climbers, amazingly gracefully can the cat here balance and select the precise footholds, and then even jump down and do a run. And the dog on the right side is also carefully climbing up these rocks here. And so this versatility, both the capability to run around, but then also do precise motion, this is a source of inspiration for us to do legged systems, to have this versatility in there as well. So now I show again this slide in the history of my lab's robots developments. I would like to spend a few minutes now in showing you what some of these robots are able to do in the past and at the moment. And I'll start with this quite old robot now. It's already 10 years old. We have a copy of it that we're still using daily. It's a copy that has this green body. This one is now not used anymore, but we've used this for many, many years, and I would like to show you a few videos here. We can see on the top left, this is a 2 meter per second trotting motion. So like horses and dogs, actually most 4-legged animals, also elephants and mice, they have gaits like a walking, crawling gait, a trotting gait, a bounding, galloping. And this gait that we're showing here is a trotting gait. You can see here also on the right, the diagonal leg pairs, they always move up and down together. And this is the gait that allows us to do very slow forward motions. So you can see here the robot is not moving forward, but it's still sort of reactive and ready. And in this particular video, it is disturbed with a 23-kilo boxing bag. We show that with our very fast motors, actuators here, we can make a corrective steps so that the robot doesn't fall down. There's also these step reflexes here that can pull the leg up in case there is an obstacle. And then in the bottom, you see a few videos of other obstacles. You see obstacles are very important for us because this is the whole advantage of legged systems, that they can overcome obstacles. Here on the bottom left, you see the robot is randomly walking over these random obstacles, and then when the foot goes up, it needs to recorrect the whole body orientation. On the right, you saw the robot was crossing a gap, getting up a few steps, and then crossing these stepping stones here in a careful manner. Here, the robot has an idea of the map, so it can optimize and plan the footholds ahead of time. So with these, maybe a detail I didn't mention is that our robot has hydraulic actuators. So there's hydraulic oil under pressure. Also, the very famous robot Big Dog is using this particular actuation, and it allows us to do very powerful and strong and fast motions here. The other advantage is also that we can do a very precise control of the torques, of the forces that are acting inside the leg joints. And then we can map that to the end effector, to the foot. So we can choose with our optimization of inside the robot brain, in which direction this ground reaction force is pointing. And we can make it in a way that it stays inside the friction cone so that it never slips. And in this particular experiment, we have very steep, like a chimney here. Michele, who developed this, he's a passionate climber, and he wanted to implement what he has to do in a chimney, also in the robot. On the right side, you see Shamel. He's showing how the robot can navigate with soft terrain. So he's actually detecting and evaluating the softness, the stiffness and damping of the terrain, and then adjusts the controller accordingly. And this works very well, and it's the first steps towards more softer terrain, for example, in a vineyard. Now, interesting for this talk here is probably that we're also using some machine learning for legged locomotion. So here we're illustrating the a map, a height map. So this map is in front of the robot where the robot will step next, and we're showing the height profile of the environment next to the in front of the foot, and in the center is where we would put the foot next. But if that foot placement is not suitable, for example, because there's a gap here, then the neural network, the deep neural network that we developed here and trained here, suggests another foothold that is safer. And that, shown in simulation here, works very well. We can see how some of the feet are stepping twice on the same point and then take a longer step to cross over two gaps at the same time. And we're doing this type of simulation with all of our controllers, and then we run them on the robot. Here on the left side, you can see 0.5 meter per second trotting, and it doesn't step inside these gaps. It can do these micro corrections in real time because the neural network is very fast. Also, if we pull the robot towards these gaps, the robot can make these micro corrections, these micro steps, to not step into the gap. Okay, let's move on to the third generation of the HiQ robot. I skipped the second one. I want going straight to the third one. This version here is very powerful and has everything on board: the battery, the hydraulic systems, the communication. And to demonstrate the strength of this robot that weighs 140 kilos, we brought it to the airport of Genoa to pull a small passenger airplane of 3.3 tons. And we managed to pull it for about 10 meters. And you can see here, the robot has to optimize also how the forces create the traction to do this stunt. Now, of course, this is not really a task that a legged system should do to pull airplanes. This was a demonstration of the capabilities of this machine, and we wanted to show something that no one has ever done before, and we got quite some media attention because of this. But the robot will be used in these applications that I mentioned to you before, where rough terrain is there. But the pulling capabilities can also be useful for other applications. So this robot, as I said, is 140 kilos, is about 1.3 meters wide, long, and it has enough payload to put on scanners, different types of sensors, even a manipulator arm, as we will see, and power tools, because there's already hydraulic pumps on board. Now, putting an arm or two arms on top of our quadruped robots was always a dream in our lab, and we had a PhD student that developed this hydraulic arm that was then mounted, that we mounted in front of our HiQ robot, and then with the joystick operation, we demonstrated how we can maybe remove some rubbles, obstacles in the way. And a bit later, we started a project inside IIT with different teams in IIT. This is together with the ADVR team and the HHCM team. And we're basically developing a system here that combines an electric arm developed by the team of Nikos Takrakis inside IIT and the virtual reality, vision, and augmented reality of Nikhil Deshpande's team, and then also a hand arm haptic exoskeleton that allows the operator to feel and teleoperate the machine in a hazardous environment. We're collaborating here with the Italian firefighters. They give us certain use cases. Here we're cracking open this plastic, we're taking out the hose, and then in another example, we're collecting precious objects, like for example after an earthquake. People can't go back into their buildings because it's not safe, and they maybe have to retrieve precious objects like jewelry or pictures. Then just briefly, another project. This is the European Space Agency project that we are together with DFKI and Airbus to put our software on how to make these legged systems walk on a hexapod robot, so a 6-legged robot, and then also on our quadruped robot to tackle much steeper environments like craters and caves where the normal wheeled rovers cannot enter. So I'm coming towards the end of my talk. I see also my time is running up. I would like to show you what we've recently done in the simulated vineyard in Piacenza. Here we brought our robot, and the HiQ robot is doing careful stepping here, just as a very first demonstration out in Piacenza. But then a few months later, we went to a real vineyard. This is a vineyard in Borgonovo Val Tidone, and thanks to the management of the vineyard, Tenuta Pernice, we were able to have 1 or 2 days of field trials with the robot in the field. And you can see here, HiQ Real has a LiDAR sensor and some other sensors in the front. And here we're showing 2 experiments. One is on tilled soil. This is a bit softer and the feet sink in a bit more. And then on the right side, we see grassed soil. Here this soil is a bit more rigid and the robot sinks in a bit less. To make it a bit more difficult, we collected a few obstacles that we found. These are rocks and compact soil, and we made a pile in front of the robot so that we can make it a bit more challenging for the robot and show better future capabilities of these type of machines inside more unstructured environments. Yeah, let this run a little bit, because then we can see how this leg here in the back steps up onto this rock, slips down, and the robot needs to keep its balance without falling down. Okay, so I would like to go to the conclusion. We saw that for certain operations in the vineyard, we cannot do a very easy mechanization, so automation is required, especially due to skilled labor shortage, and to increase overall sustainability and efficiency in the vineyard. Then selective vineyard operations, they need AI, data, and robotics to automate them. And to conclude, in the VINUM project, we address winter pruning of grapevines. We use neural networks for pruning region detections and segmentations. We then do a graph construction. We also have mobile manipulation for cutting the old canes, and with this mobile manipulation, we also need to understand how to move the body in the correct way. And we have legged locomotion for rough terrain navigation inside the vineyard. So the image again on the right, this is the currently ongoing work where we integrate all the systems together, and we will test that in the next winter pruning season, which will start in winter. At this point, a few words of thanks. Of course, the Università Cattolica experts in viticulture that collaborate with us, the team of Faye and Darwin Caldwell, and my team that made all this work possible. There's a website, vinum.robot.eu. It's not always updated, but go and have a look there. There's our papers are written there. At this point, I would like to take some questions.
Oh, thank you very much, Claudio. Thank you very much. It was, wow, I'm personally completely impressed, and because it's amazing to see this robot pulling a plane, and on top of it now going even in July through this, through this vineyard, over stones, no? And yeah, it's amazing. And that was my question I had in the beginning. Are you also aiming for steep hills, like vineyards,
Yes.
like in Germany at the Rhine, this kind of typical too steep vineyards? Is this also maybe one day a use case?
Yes, absolutely. I think that's where one of the main advantages then of the legs come in as well, because the other vehicles might topple over, but in the robot with legs, you can really go low and keep the balance active, even if there's some steps in there as well, which is often the case. We don't realize as humans, but the steps are a big problem for the machines. But for us, it's just daily work.
Yes. So I have here some questions. Again, all you participants listening to Claudio, please write in your questions. I have some here. We are waiting for your questions, but I'm starting now. It is not completely clear if this is a European project VINUM or a national project from Italy.
Yeah, I haven't explained it well enough. It's not an EU project. We don't have any EU funding for that yet. It would be nice to get some. This is mainly the collaboration between just IIT and Unicattolica that decided to do a collaboration with internal funding. We have, well, Unicattolica has some national funding as well from the Pruning funding network, but this is mainly internal funding so far.
Yes, so, but secondly, are you the father of the idea? Are you the driving motor, or is, I mean, I see a team here, of course. You have the last slide, you think all the people, but is it, you feel like you're the father of the idea, or is it a team?
No, this is actually a technology pull. So we're not pushing our technology here into the application. This is really coming from the viticulture experts that talk a lot to the farmers, and this is really a need. And they met up with us because there was a bigger collaboration between Unicattolica and IIT, and we started to talk to the Vineyard experts, and they told us what their problems are, and we told them what we can do with our machines and what are the possibilities. And that's how the idea was born together to define, okay, this can be achievable in the next years.
Okay, thank you. And the next question is, what is your plan next? I mean, we understanding now you are going here further, but what would be your next step to make this even more, maybe the next project?
Well, so first of all, we need to do the integration of these subsystems that we've seen today, and then demonstrate the whole pipeline working. This is certainly not easy because there are many unpredictable things happening, and in real life you also have much more challenges as well. We're trying to foresee what kind of challenges there are. That's why we're bringing the subsystems already into the field, so that then the integration is a little bit easier. So what I think is very interesting is that these kind of basic building blocks are very modular. So the segmentation approach can be very easily retrained for other types of crop, or other types of fruits.
Yes.
And the manipulation on the robot legs can also be very easily reused for other applications, even outside of agriculture. So I think all these building blocks, that's where the beauty comes in. So if there's another technology pool where someone says, hey, I have this problem, why don't you put these elements together and then we address something new?
Yes, thank you. And that leads basically again to a question which I have. This is maybe a little bit political, but I mean, seeing what you're doing in the vineyards, I mean, how do you think this combination of AI and robots and big data, of course, can solve these critical and complex problems of the world's challenges, like prevent hunger or climate change? Do you have an answer?
Well, you're hinting to the Sustainable Development Goals that the UN has put out. We actually have an ongoing scientific initiative inside IIT, where about half of the teams are working together in parallel to the other activities to put together their technologies and addressing some of the Sustainable Development Goals. For example, SDG 2, the number 2 of this goal is zero hunger that you mentioned, and my team is involved in that with the work that I showed today. And other teams are working more on bioplastics, for example, out of waste, so that they can be reused for packaging or on the field again. I think the collaboration inside big institutes like IIT is needed to have this cross fertilization between different teams at different sectors to make this happen. But I think also the EU is doing a good job in having a lot of funding for EU proposals where EU projects where these different expertise are coming together. Now, to specifically address the sustainability with AI and data, we've seen it, we share our data set, for example, it's part of the academic efforts in not just sharing scientific papers and results, but also sharing the data sets, because annotating all these images is days of work. I think annotating one image by an expert takes about 20 minutes. Yes. And of course, we as an academic society, we need to share these results, and other people can then use this data set and retrain much faster and advance faster.
Yes.
Yes, I'm wondering if there's any funding on a UN level for research projects where then also not just the continents can work together, but I mean the EU is working nicely together, but also in a more world scale. That I don't know. Maybe foundations like Bill Gates Foundation or other foundations can do that on a global scale.
That's basically, it is the missing part. It's there now we learned from Corona. It's probably the fastest way if you would work together in the pandemic attack. So, but the same in other global problems like hunger or just energy and climate change. So yes, it's a missing, I think it's still missing UN global funded research, but I think that's why I'm also in the cafe. I hear more and more people would do that. And so it's a need. And there's this SDG UN conference from the 22nd to the 24th of September, where all these global researchers meet. I make a little bit advertisement. 22nd to the 24th of September, online of course, and worldwide, all researchers interested to work together are there. And of course, then also the point, we need more funding. And in the moment, mostly, as you said, foundations do that. They give money in, but it has to be thought about if it couldn't be different. Here comes the more practical questions. After all my political blah blah. Peter Reibaltowski. What is the energy source of the robot? Could it deliver continuous work?
Yeah, that's a good question. At the moment, we use a battery. There's a lithium polymer battery that has a lifetime that can is currently limited, but there's these charging stations where these robots can go and sit on, and then after some time the battery is charged again and they can continue. And we can also think of having an automatic battery replacement station where the robot goes and gets this replacement done. So yeah, I think you know, in the quadruped robot research domain, the very, let's say, the most famous not the first one, of course, but maybe the most famous one is Big Dog. Big Dog from Boston Dynamics had a combustion engine on top. And of course, with gasoline, you can last much longer with, I don't know, 3 liters of gasoline than instead of 3 liters or 3 kilos of battery, you can last much longer. But the research community went a little bit away from gasoline because there's a trend in electrification of all the machines, and also to use them inside the lab, and in general, the batteries are much more quiet and less polluting. But I think if the battery technology doesn't catch up as fast as needed, and we know with all the autonomous driving cars and Tesla pushing for always even better batteries and many other world players, I think the autonomy will be sorted out with batteries.
Mm-hmm. Yes, and I have 10 more questions, but that's it. The cafe is already closing down. As always, we are on time. And this is like, we have 1 minute to say again, thank you for everybody here being today with us in the cafe. And please, if you have an exciting work to share, tell me, and apply as a speaker yourself with your project if you like. Now back to you, Claudio. Thank you very much. It's totally exciting. I'm a fan of, I will keep myself informed.
Thanks a lot, Carmen, for the invitation, and thanks for AI4EU for making this possible. I think it's a great webinar, web cafe series.
Yes, and thank you for coming. It really lifts off a great speaker like you, and it's totally exciting to see, you know, how it's moving on and how we soon have our robots in the steep Rhine Valley where I'm coming from. So yes, thank you very much. Have a great day, and everybody enjoy the afternoon, and bye-bye. Thank you.
Bye, everyone.
Bye-bye.